In this video, we're going to talk about apportionment. So apportionment is something we do see in our lives, like, for example, how we determine how many representatives each state has in the House of Representatives. Or even, let's say you have a bunch of school buses that go to multiple districts, how you divide that up based on the need and student population at each district. So apportionment helps divide that up. So here's the rules for apportionment. The people and items can only be divided into whole numbers. Otherwise, it wouldn't make sense to have a half number. So in the end, whole numbers is what's going to be our deciding factor. We must use the exact number of people or items that we are dividing. So it has to be exact. Each group must get at least one. And the number of people or items assigned to each group should be proportional to the size of the group. So those are the basic rules of apportionment. So these are the steps and the methods we're going to use. They're kind of hard to read like this, but we'll refer to them as we go through each one. First thing you have to do is find a divisor. And this is the number of people each person should represent. And it's gonna often be a decimal. And then we divide the population by the divisor to get what's called the standard quota. And that's going to be like our starting point when we do these methods. Hamilton's method cuts off the decimal that we get when we do our division to find the initial, or what we'll call the minimum number, and then give extra seats in order of the highest decimal remainders. So let's talk about what that looks like in an actual example. And then we'll go through all four of these as we kind of work through this real quick. Interestingly enough, in our history, there was a compromise in apportionment that happened between the North and the South, where a slave was counted as 3/5 of a person. Now, anybody who has a little bit of history background understands that the South wanted slaves to be counted as a whole person. They weren't letting them vote, but they wanted counted as a whole person. So that way they could get more voting power. The compromise the North gave was that they would give them a 3/5 representation. And that ended up kind of undermining what the South was wanting to do, hoping to see more voting power, but it wasn't enough to give them the voting power they had wanted. So interesting kind of information about our own apportionment and how it was looked at, where it violates our first one, which is that whole numbers were used. Okay, so let's say PCC is a large college and they have 4 campuses and they have in their budget 45 full-time instructors for math. And they want to make sure they divide it up into the campus fairly so that they have good representation based on the student population. So let's approach this using Hamilton's method first. So the first thing we need to do is create a divisor. So you're going to want to get your calculator out because this uses a lot of calculation and you're going to have to kind of keep up with me dividing. You may have to pause the video every once in a while, do some division and double check your work against mine because that's an important piece of these. Okay, so here's what we're going to do. We're going to first find out the total number of students there are at this time. So go ahead and add those 4 together. And when I did it, I got 23,231. All right. So what I'm going to do then is, because I have 45 faculty members, to create a divisor, I'm going to figure out then about how many students I should have per faculty member, or for each faculty member. So dividing that, now get your calculator, do this division, double check it with my numbers, make sure you're matching with me. I got 516.24. So there's my divisor. So what I've literally done right now is the very first step here. I found the divisor. It's the first thing I've done. Now I'm going to find the standard quota. This is when I divide the population by the divisor. So I'm going to take each of these student populations at each campus and I'm going to divide it by 516.24. Divided by 516.24. And you get your calculator and start doing this. Here's what I got. I got 17.18. I like to include a couple decimals. for when we're figuring out remainders. 9.38, 13.17, and 5.27. So there's the standard quota. That's the second step. We just figured out from the divisor the approximate breakup of the population using the divisor. Okay, now here's where each method kind of comes into play. Hamilton said, cut off the decimal. Just start by cutting off the decimal and see what we have. So the first one would be a 17, a 9, a 13, and a 5. So no rounding, just cut off the decimal. Okay, so right now, this totals up to 44 people. If you total that up, it's 44. It's not 45. So if it had been 45, we'd be done. That would have been the final breakup for the campuses. 17 to Sylvania, 9 to Cascade, 13 to Rock Creek, Southeast 5. But because we only have 44 and we need 45, we have to place the final person. So Hamilton's method says, place it by the highest decimal remainder. So looking back at the standard quota, that would be Cascade. 0.38 is higher than all the other decimals, so it has the highest decimal remainder, which means I will add the extra to Cascade. So my final would be 17, 10, 13, 5. That would be the breakup, and that does total up to 45. All right, so that's Hamilton's method. Pretty simplistic. Let's go ahead and read Jefferson's method. So Jefferson says, cut off the decimal and then lower the divisor. So if cutting off the decimal doesn't work, then lower the divisor so that there's no leftover seats. So in other words, rather than reassign based on remainder, they say change the divisor so that when you cut off the decimal, it works. So that's how we're going to approach Jefferson's method. So thankfully, they start the same. The standard quota is going to be exactly the same. We'd have 17.18, 9.38, 13.17. Doesn't look like a point. Sorry, it's kind of floating in the middle of the air there. 13.17 and 5.27. Okay, so those were our standard quotas. We had the same divisor of 516.24. Okay, now, initially, same initial as it was with Hamilton. We would go 17, 9, 13, 5. But unfortunately, that's not enough. So we're going to lower the divisor to see that when we cut it off, if we would get enough. So since our divisor is 516, I'm just going to use a nice round number. I'm going to change my divisor to 500. So I'm going to divide everything by 500 instead. So pause the video, do this division, okay? See if you match up with me. When I divide the first, and I'm going back, by the way, to this column. I'm dividing all of these again. New divisor now, new divisor, okay? So I'm dividing them all by 500 instead. So when I divide by 500, I get 17.74, 9.68, 13.59, and 5.44. So this didn't do anything for me because none of the numbers changed enough so that when I cut off the decimal, I get a new result. So this one doesn't work, but I notice this first value is very close, right? In Sylvania, 17.74, we're getting close to jumping up to the next level. It would be a higher number. So I'm going to lower my divisor, but I don't want to go too much. I'm going to lower it to 490. So if I jump down to 400, it would be a big jump and everything, it would add up to be too much, okay? So I just want to go a little bit. So I'm going to divide everything now by 490. So sorry, I shouldn't have erased it. These same highlighted numbers again. I'm going to divide those all by 490. Okay, so this time, pause the video, calculate it. I'm getting 1810, 9.88, 13.87, and 5.56. So, phew, I did it. I was able to only make one of them change for cutting off the decimal. So now, if I cut off the decimal, I would have 18, 9, 13, 5. That totals up to 45. And that would be my answer. That's how I would divide it. So here I'll write the word final, like how I had above. So that's how a lot of the methods work after this point. So if you make too big of a jump, you might end up having too many numbers round up, right? Go higher, and you would end up with a total more than 45. So, since we have our calculators, don't feel like you have to do giant jumps to make things work. All right, let's look at Webster's method. Webster's method's kind of similar. But instead of cutting off the decimal, they actually round the decimal like normal. So they do a normal rounding. All right. So that then looks like this. Same standard quota, same divisor to start. Now let's see how it would look different if we're rounding the numbers instead of just cutting off the decimal. 13, oops, sorry, a little bit low. 13, 17, and 5.27. Okay, actually none of them round up. So unfortunately, same issue, even if I was allowing rounding. Okay, but here I'm going to change the divisor again, but I kind of already know what's going to happen when I divide by 500. Oops, because I did that up here. I divided by 500. And when I divided by 500, too many of them round, right? The first number is going to round up to 18. This will round up to 10. This will round up to 14. So I'll be too high. So I need to go lower than 500. I'm sorry, higher than 500. Not such a big jump from 516 to 500. So how about I try 510? Sorry, it's doing a weird thing. I apologize. Here, let me try to get rid of it. Boom, so I don't have to see it. Okay. So I'm going to divide by 510. So here's what I get. Pause your video, do your dividing, see if you match. I'm getting 17.39, 9.49, 13.32, and 5.33. Darn it. Not enough to make one of them round. Okay, but I'm super close. So I'm going to just do 509 instead. 509. Okay, dividing by 509. So once again, pause the video, divide them up. Again, and I'm dividing these. I'm always dividing these by this new divisor here of 509. Okay, so dividing, I'm going to get 17.43, 9.51. Oop, we got that one. 13.35 and 5.34. We did it. So that 9.51, that one's going to round up. And that's going to give me 17, 10, 13, 5. So there we go. That totals up to 45. And that's how we would break it up. Happens to be the same breakup we would have gotten for Hamilton's method. Okay. All right. So all of those are pretty simplistic, just changing the divisor, which is a little bit annoying, but that's kind of how they did it. Let's read the last method. And this one gets a little bit more complicated. So Hill-Huntington is the one we use now. So this changes how we divide. I'm sorry, how we round. So instead of rounding using the idea that you could round by 0.5 or higher, right? Those are our rules of rounding. If it's 0.5 or higher, we round up. If it's 0.4 or lower, we round down. But rather than using that, they use something called the geometric mean, which says that we are going to round based on different numbers. We'll round up based on a new number that we're going to calculate with this formula. So let's go see what that looks like for our example. So let me scroll all the way down to the next page. And I gave myself some space. So same divisor, 516.24. Same initial or standard quota, which is 17.18, 9.38, 13.17, and 5.27. Okay, so these numbers give us the X in our formula. So in our formula, oops, sorry, I tried to switch to green. In our formula, this X comes from the initial amount. which we had for Hamilton's method. So cutting them off. So x equals 17, x equals 9, here x equals 13, and here x equals 5. So those x's change based on the location. X changes. So in this formula is going to be done for every location, and every location is going to have a new number they use for rounding. So here's how it looks for the geometric mean. So Sylvania, I'll just use SY to represent, or SYL to represent Sylvania. If I take x equals 17 and I do, 17 times the square root of, oh, I just realized I wrote the formula wrong. I was like, that doesn't look right. Sorry, it's actually x times x plus 1. My bad. Okay, that makes more sense. So plugging it in, we get 17 times 18. And then you take the square root. So plug that in your calculator, and that gives me 17.49. So this, if a number hits 17.49, I'm now going to round it up. Even though it's not 17.5, 17.49 is enough for me to round it up. Okay, let's look at Cascade. For Cascade, their x was 9. So 9 times 10, plugging that in, taking the square root, I get 9.49. So that's my new rounding number. Rock Creek, here I'll just use RC. That is 13 times 14, which I get 13.49. So it's not really changing the rounding number very much. Normally I would round if it hits 17.5 and then I round up, but now it's 17.49. So it's not changing it by very much. But when we're doing these divisors, that might be enough to bump it up. And then Southeast, that's 5 times 6, which comes out to 5.48. Okay, so that one actually came out just a tiny bit different, a little bit lower. So these are how I'm going to round my new rounding numbers. So I'll round up if any of those numbers show up when I'm doing my divisors. Now, I happened to do a divisor earlier. Let me scroll back up here. Of 510, and I want to look at it. So here, let me erase all my other highlights so that you can see where I'm focusing. So right here, I'm focusing right here. I'm going to rewrite this one below. Pretend I, hadn't done this already. I try 510 as a divisor, and here's what I come up with. 17.39, 9.49, 13.33, and 5.34. So under the previous method, I'd have to lower my divisor to make it round properly. But under this method, Cascade can round because it hit 9.49. So this gets to round up to 10, and everything else does not. Nothing else rounds up under the new rounding rules. So this method allows me to round up sooner, so I'm spending less time doing these divisors. That's how the Hill-Huntington method works. But it is a little tedious coming up with this new geometric mean. It takes a little time, but it allows less work on the devising method. Okay, last little bit. Happens to be that the actual breakup of the campuses looks like this. Oops, I switched to highlighter and it didn't work, sorry. Looks like this. So the extra person, in none of the scenarios did the extra person end up going to Southeast, but the extra person actually did end up going to Southeast. And it had to do with they were a specialized position, and that's why they went there. So that's the breakup. Now here's voting power. So voting power means based on the number of full-time instructors at the campus, how powerful their representation is for their students. So the idea is that a faculty member represents a certain number of students, and the smaller number of students that each faculty member represents, that means that they have more representation. That particular campus has more representation among the faculty than the other campuses. So let's look at the voting power based on the fact that this is the actual setup at PCC. So what we're going to do is we're going to take the students per faculty member. So when you see that word per in math, that means divide. So I'm going to divide the number of students by faculty members. So I'm going to divide all of these. So get your calculators going again and start dividing. I get 492.83, 605.13, 522.85, and 453.67. Hopefully I did that right. So what I'm seeing here is that the worst representation happens on Cascades campus, right? They have so many students per instructor. So they have the worst representation when it comes to picking like curriculum and textbooks. But the best representation happens at the Southeast campus. Those students are getting the best representation among the faculty when they do voting on things like textbooks. And that's how voting power works.